Hello everyone, do you hear me? Okay, so welcome to this webinar for the Aidge framework. Hello everyone. I propose that we start. So we will first do a quick presentation and recall of Aidge goals and ambitions. And then we will have about half an hour for a demonstration, a live demonstration of some of the framework's features. And towards the end of the presentation, we will also have two industrial testimony from Thales and INRIA. And we will finish with a question and answer session for about 15 minutes at the end of the webinar. So you will be able to ask your question in the chat, and we will try to respond to your different questions. So I propose that we start just by recalling first what is Aidge, what are its design goals and ambition. So let me start on that. So as you probably already know, Aidge is really designed to be an end-to-end framework, which is highly interoperable with the different existing standard and deep learning frameworks, so mostly ONNX, NumPy, but also PyTorch and Keras. It's also intended to be a modular library with light modules. Each module is dedicated to specific tasks. And we also designed it with the fewest possible dependencies, so to allow any user or developer to just take what he needs for his goal, and do not have to load a huge framework and tons of modules just to accomplish a simple task. I also recall that Aidge is in open source and currently hosted by the Eclipse Foundation under the EPL2 license. And of course, this framework is supported by French initiative and also a European project, and a large ecosystem of academics and industrial. So let me now just talk about the main key features of the frameworks, some of the key features of the framework. So I have three main points. So the first one is high-level application optimization, where we want to integrate in the framework well-characterized and state-of-the-art optimization. So the goal is really to be able to propose traceable, step-by-step automatic graph transformation. So that are really traceable, meaning you can really master each step in the process of accountization, for example. That will also ensure that you really master what is going on, that you will be able to reproduce the results, and have support and maintainability on your quantized model, regardless and independently of the hardware provider that you use. And one other important point is that we want to provide in the framework detailed quantization scaling strategies that really go much further than just faked quantization that you already can have in other framework, but we really want to go to fully quantized model using integer data representation or binary data representation in case of binary quantization, and so on. And of course, we also want to propose the state-of-the-art algorithm for post-training and quantization-aware training from 1 to 8 bits in mixed precision. So you can see that some of these features are still on their way and will be available in next year, during the next year. And and we also have compression features that is, you have modules dedicated to that you already can have access in the GitLab, which is a tensor decomposition for compression, where we also reach state of the art in compression. If I go further, on the main key features of Aidge, we also want to propose innovative graph editing and scheduling. So in the framework, we have a consistent intermediate representation that has the characteristic of being usable at different level of granularities, while ensuring that you have a strong equivalence guarantees between each transformation steps. So in the framework, we also have a powerful graph matching capability. So that really allows you to match any kind of operator or subgraph in a graph and transform it. For example, you can replace it with other kind of operator. You can change the granularity by fusing or expanding operators into coarser or finer grain operators seamlessly in the framework. Another innovative feature that we have in Aidge is the ability to model the producer-consumer of each operators. So you are able to model how much data is consumed and produced at each execution step of each operator, independently of the actual implementation of the operator. So we have a transaction level modeling like features into Aidge that allows you to statically schedule a computing graph, even if you don't have the full implementation of the operator. In the next year, we will also propose a feature that will allow you to really mix different coding type and different implementation paradigms in the framework. For example, spiking neural networks or full data flow modeling. For example, the ability to schedule operators that are really data flow operators, don't consume a full tensor at each step, but for example, just consume a line of a tensor at each step and so on. This will also get you closer to dedicated hardware implementation. And lastly, among the key features of the framework is the ability to generate efficient code, of course, for embedded targets. So Aidge is also a rich toolbox for operators optimization and hardware mapping. The goal is to offer many tools to easier the creation of specific implementation or to use third-party kernel libraries more easily directly in the framework. We will also have an integration with other machine learning compiler stacks in order to generate really optimize the operator or subgraph with a compiler, with a dedicated compilers. And we will also want to offer some certification constraint in Aidge, which is also a specificity of the framework. And all of that, of course, in a very interoperable way through ONNX, full import and export of model at each steps in the process of deployment of an application. And at the end, the goal is really to be able to develop new architectures also based on Aidge, on the Aidge framework, using its code generation features to transform a graph and directly generate RTL representation of the graph for hardware acceleration, which is what you have done with the neurocorgi ASIC accelerator, which we have a demonstration currently running and which was generated by Aidge. So now I propose that we switch to the live demonstration of the feature of the framework. So we will go more deeper in the way it works with some live example, and I will let Cyril Moineau
Hello.
Take the lead.
I don't know if it's working.
Yes, we hear you, Cyril.
Okay, perfect. So I will share my screen in just a minute. Okay. So let me know in the chat if you see the presentation I'm doing. So I will present the notebook. Okay, perfect. Thank you. So I will present a small demonstration, which is based on the tutorial 101 that we developed for Aidge. This tutorial will have extra steps that we are working on and that we didn't release yet in the tutorial 101. We will also present some other features that we haven't been able to present yet. So, and that will be available in a future release. We will deploy the notebook. I think we'll make them available. Yeah. So this demonstration is mostly based on the MNIST dataset and on a deep neural network, which is based on a multi-layer perception. We will also present some other more interesting features, but the goal is mostly to have a red line to follow during this presentation. So we will feature the different keys features that Olivier talked about. First, we will set up the notebook by defining some visualization functions. So such as, because for Aidge, we use a mermaid format for saving graphs. And so we will define this function, visualize mermaid key, which allow to visualize the graphs. So as Olivier said, Aidge is a very modular lightweight framework. It is based on the core framework, which contains all the graph API and different core operators, as with also some other functionalities which are not that important for the purpose of this demonstration. We will also have multiple plugins. We will talk about the export plugins, which allow to generate code, which is the main feature of the Aidge platform. So we can generate generic C++ code, ARM-based code, and TensorFlow, for example, but there's other export plugins that are being developed. We also have some backend plugins which allow to run the inference on your computer while you're working on your neural network model. We have some optimization plugin, quantization compression, which will be featured in this demonstration, and the ONNX plugin, which allow a seamless integration with ONNX saving platform. So first, we will import Aidge. By doing so, we have access to convolution operators. We have access to tensor. And when we look at the available backends for these operators, we can see that convolution already have an export backend, but the tensor have access to a CPU backend. So the tensor has access to a CPU backend in order to store data. But the convolution don't have access to any CPU backend. So that means it only have access to an export backend. That means that right now, I don't have any implementations to run my convolution with. So in order to get an implementation, I will import Aidge backend CPU. And just by running this line, you will see that I have access now to a CPU backend. So this is how the modular platform comes. It comes with multiple package which can be imported using import from Python. For the rest of this tutorial, we'll also use Aidge ONNX. We'll use NumPy and Matplotlib for plotting data, and like the pictures we will infer on, and NumPy to load the pictures. So we'll import this. So for the first element of our toolchain, we will work on the import ONNX. Aidge proposes high interoperability with ONNX. We can load a lot of different state-of-the-art models, and we propose a very unique fallback mechanism to generic operators, which allow to never fail loading a model. We also have a clean management of subset, which come in handy and which is not always the case for every framework. So let's start by importing a model. So we have a MLP model for MNIST, which we can just load with raw inline. As you can see, the flattened layer has been imported as a generic operator. This is because we don't support flattened layer as we don't need it, because our gem operator, which are also named fully connected, so FC for short. So the FC layers already treat data, contiguous data, so we don't really use the memory. We don't really need to change the memory layout with a flattened layer. So this is why we don't support it, and we will see how we can deal with it. So if I'm using now the save method, I can visualize my graph using Mermaid, and you can see here the flattened layer which is imported with dot lines, which represent the fact that it is a generic operator and it's not an operator I will be able to run. However, I will be able to manipulate the graph to make it run. So here we have our really simple graph with three FC layer and 2 ReLU. So talking about graph transformation, one of the really key feature of Aidge is powerful graph search and replace engine, which is the graph manipulation. So we developed a syntax of regular expression, which allow to easily select a part of the graph, a subpart, and to improve it and replace it easily. For example, so we do this by using what we call recipe. An example of recipe is a fusing convolution and batch normalization. So we can just fuse these two operators into a new conv. And so Aidge come with a set of ready-to-use high-level transformation, which are called recipes. Some of these recipes are, for example, so the fuse batch norm. There is the matmul to FC, which allow to fuse mat multiplication and addition operation into a fully connected operator. We have the conv or horizontal tiling, which allow to replace the convolution by a subgraph of tiled convolution. We can use remove flatten, which we will use in this tutorial to remove the flatten if they are before FC layer. We have also some interesting ones, such as adapt to backend, which allow to add transpose layer to match the expected input and output data format of an operator. This is very interesting if in order to easily adapt the graph to the backend we select. Because if we have a backend which has NHWC instead of NCHW, then we want to adapt it, the input tensor, and we can do this with just one line, adapt to backend. And constant folding, which is one of the key features, for example, of ONNX Simplify, which allow to remove constants by computing them. So all of these are one-liner graph transformation, which you can easily use in Aidge. So how to use a recipe? You simply call it on your model, and that's it. So here I call it, and when I save, I see that the flattened layer has disappeared, and all the operators in my graph are runnable. So I can do something with this. You may not be very impressed with just this example, so I propose to see a more complex example. But first, I must introduce the concept of meta operator. So as I was saying, talking about the linear layer, which is the equivalent of the FC or the gem layer, it can be seen also as a mat multiplication and followed by an addition. And Aidge introduced the concept of meta operator, which allow to choose which granularity you want. Do you want to see this operation as just a linear operation, or do you want to see it as a math multiplication followed by an addition? Using meta operator, you can embed this subgraph into one operator, or you can expand it into multiple operators. You can easily choose and replace part of your graph this way. And we will see this with the Dino V2 model. So if you ever try to load a Dino V2 ONNX model, you will see that there is a lot of different operators, atomic operators. If I just scroll through all the operators I'm loading, we can see there's a lot. And it's not very human readable because as human, we would prefer to see multi-head attention. We would prefer to see layer norm operations. And Aidge allow to easily fuse operator into one operator using meta operator. So this is what those lines are doing. This is when I was talking about the graph regular expression syntax we developed. This is it. This allowed to easily match a subgraph into our Dino V2 graph and to replace it with a layer norm. This way we have a more human readable graph, but also this means that if I have a very performant implementation of the multi-head intention, I can replace all of these operators by just one very fast implementation of the multi-head intention. So this recipe simply is called fuse to meta operator. You give your model, you give the regular expression you want to match, and you give the meta operator you want to fuse your subgraph into. So I will just run this. For performance issues, I will not print it because, as you can see, the Dino V2, which is here on the left, the row Dino V2 is pretty unreadable. It's a lot of nodes. And here you can see the Dino V2 after the fuse of all the layers, which is much more humanly readable, but not readable in a notebook yet. So this is why I print it like this, like so. So here you can see that with Aidge, powerful graph matching, you can easily switch from one representation which is unreadable to something that is much more workable. An example of thing we can do with the Dino V2 is try to do some static analysis to find bottlenecks or the number of parameters we will use. So Aidge come with a static analysis framework, which is in Aidge core. The static analysis methods can be easily used just as the same as a one-liner, basically. So you just have to instantiate a static analysis object, and with the summary operation, you will be able to see. Oops, I just do scroll. You will be able to see here the results. So basically, a summary of our network, Keras-like. With the output dimension for each layer and the number of parameters. And so here you can see our representation with layer norms, multi-head attention here, and this is much more readable this way. Another representation we have is also a graph with all the number of operations. And so here you can see that with Aidge, we can see all the number of here. So in orange, it's the number of floating point operations. In purple, it's the nonlinear operations. And so we don't have any integer operation yet. So with this, you can easily see where is the bottleneck of your network. So here we see it's mostly the multi-layer, multi-head attention and the layer norms, which are mostly the bottlenecks. Once we have loaded our network, we've transformed it, and we've done some static analysis, we can begin to infer on it. So in order to do some inference, we will go back to our use case of MNIST. To do so, we will load the image with NumPy, as we said. So this is what just I'm going to do. So numpy.load and matplotlib to show the image we load. So we're just loading the digit 7. And we can load also a tensor containing the output of the PyTorch model that was used for this tutorial. So we trained the PyTorch model and we export it to NNX. That's what we loaded before. So this is the expected output. In order to run the model now, we need to transform the NumPy input we loaded into a Aidge tensor. You can do so simply using the constructor of tensor. You just provide the digit, which is the NumPy array, and it will automatically convert it to Aidge tensor. So this is what we're going to do. And as you can see, we just loaded an input. So one channel, this is normal for MNIST, and 28 by 28. Now that we have our data, we can configure a model for inference. So as I was talking about backends later at the beginning of the presentation, Aidge propose a graph structure which is not tied to any implementation. It's just a graph representation. So now we need to link the graph representation with the implementation. And to do so, we use this function compile, which basically sets the data type, set the backend, and forward the DIMs so that we can have the output DIMs for each layer. So here we will set the CPU backend with a floating point 32, and the dimensions of the input are 128. So we'll just run this to prepare a model. And now our model is linked to an implementation, so we can run it. But first, we must create a scheduler. So Aidge uses a simple scheduling method using a consumer producer scheme. So in this case, for a sequential scheduler, the scheduling system will simply do a topological sort. And this is what will be returned by scheduler, but there is many more scheduling strategies that we have, such as, for example, parallel scheduler. So once we created our scheduler object, we can simply run forward with it and provide input data. And once this is done, we can retrieve our output by parsing the model outputs nodes and simply get the output Aidge, which is a tensor containing the output. And so we retrieve here the output tensor, which is the same as the output tensor we saved in NumPy. This is also guaranteed by the assert done here. And so, yeah, we have an Aidge prediction of 7, which was the digit we loaded here. So it is possible to save the scheduling diagram using a mermaid again. This is very important for us because we wanted to provide a framework which was a clear box so that you can always know what you're executing, what you're running. And so here we can see the execution time of each layer in my computer right now. So this is for example, the first layer was the one which took the more time. It's normal. It's the one with the biggest input. And so this allowed to easily also see the execution time for any network that run on Aidge with this function, safe scheduling trigger. So now that we've been able to execute and infer a model with Aidge, we may want to optimize it. Aidge proposed multiple optimization framework and methods. We want one of the most important aspect of Aidge is that when you want to optimize your model, you oftentimes when you are dependent to the tools given by the hardware provider. And so that means that you can hardly reproduce the performances you get. For example, if you work with a TensorRT, you will be forced to use the TensorRT SDK, sorry, and the TensorRT SDK will force you to use their quantization method. And if you want to go to another hardware provider, for example, Qualcomm, you will be forced to use their quantization, which means that for the same network, you're not guaranteed to have the same performances for your your inference with the hardware. And so Aidge allow you to ensure the reproducibility of your optimization by having one framework to export to multiple hardware targets. So first, before doing any optimization, I will just clone my model into another one, which I will call quantized model. So the optimization I will showcase here is the post-training quantization. It's a type of quantization which easily allow you to go for 8-bit quantization. The main downfall of this method is that if you want to go below 8-bit, it may not be suitable, but it's very fast and it allows you to deploy very easily your model. So as we will see, it's very easy to use, and it's very fast to get an 8-bit model in terms of inference time. So I will just run this cell. I will go very briefly on it. It allows to load in an array the different tensor that we will use for quantization. So once we've loaded all the different image we will use for quantizing our model, we will load the Aidge quantization model and use the quantized network function. So quantized network function just take a model, the number of bits, a list of tensor to use for calibration, and then there is different parameters and arguments I will not detail in this presentation. And simply by doing this, you see how quick it is. For there's a little, like there's 100 sample here. So I have now a quantized network, and we can visualize it easily with Mermaid, and we can see here that scaling operators appeared. And so here you can see that there is a float32 data for weight and biases still, and also for the activation. It's normal because right now the model is only fake quantized, which means the data are stored with a float32, but the dynamic of the data is 8-bit integer. So basically the values are int 8, but they are stored in the float32. But this is what most of the frameworks, like for example PyTorch, this is what they're producing. And with Aidge, we aim at easily going from this graph, which is fake quantized, to a true quantized graph in the framework to have a bit accurate inference in the framework. So this was a first example of optimization method. Many more optimization are coming. So the first one I'm going to talk about is the quantization aware training. What I showcased, as I said, was post-training quantization. Quantization aware training perform an inference and training. Sorry. So it performed training in order to train the model for low bits performances. Here you can see for MobileNet V1 with ImageNet, we can go as low as 1 bit for the weights and 8 bit for the activation, and we still have relatively good precision relative to the compression ratio. And as you can see, we can go as low as dividing the memory footprint by 10 and still achieving minimal loss compared to the 8-bit quantization. So this is coming in a future release very soon. Another thing which is already available is the Tucker decomposition, which is a kind of tensor decomposition. So the goal of this method is to approximate a convolution kernel or a weight for a linear layer and so they approximate this matrix by a smaller one, which allow to compress the model. For this, we compared ourselves with AMET. AMET is a framework compression used by Qualcomm. And so we can see that we get relatively close results and even sometimes better results for some compression ratio. So now that we've talked about all the optimization we can do, let's talk about how we can export the model once it is quantized and compressed to our hardware targets. So as I said, one of the main appeal of Aidge is to be able to target different platforms with one single framework. Aidge support two types of export, I'll say, the code generation one and the proprietary tools one. With the proprietary tools export, what we are doing is we are providing an ONNX to the hardware provider SDK. For example, this is how we handle TensorRT. And then there's the code generation one, which aim at producing C++ code, which you will be able to compile and run in your tool chain. For example, if you have already an application, you will be able to easily integrate our model with it. So there is here two type of code generation export. So we'll talk about the serialized export. So the serialized export is a kind of export which generates using a C++ Aidge API a model. The goal of this export is to be able to reuse the backends we've been using previously in this notebook. And so you will be able to reuse your backend with a very minimal setting. This is very useful if you want to do applications such as enabling learning on your hardware targets, because you will be able to access all the learning functions from Aidge. And why I say it's minimal, it's because if you load your model with ONNX, you don't want the ONNX loading modules on your targets. You just want the loaded model. And so this allows you to just export the C++ code and have a very lightweight export of Aidge and the use of Aidge directly on your target. And the other code generation method is the generate C++ project of kernels. So this is what we're going to do, and this is what we've done in the past. This kind of generation also generates directly the kernel, so we will not use the backend anymore, and we will have a very standalone and very lightweight project. To generate an export, first I will just remove any previous exports. So as you can see, I don't have any folder called my export. And I will import the export CPP module. Using this export CPP module, I will be able to use the scheduler export function. So the scheduler export function take as an input the scheduler. It you have to provide the path of the folder you want to generate and the library, the export library you want to use. In our case, it's the export lib C++ for generic C++ code. And then we will provide also a memory manager with some args, such as the folder of the stats of the memory manager. And we will also provide we will also set wrapping to false. So here I just exported my my model, and you will be able to see if we look at my export folder. You will be able to see all the files generated. So I just make this scrollable. We generated a makefile. We generated a forward.hpp header, which declare the forward function. We generated some kernels for the relu, the FC, and also max kernel. And in the layers folder, we generated all the attributes of each node. Then network is here for some utils functions, and parameters exports the different tensor for weight and biases. Forward.cpp generates is a function that will run each kernel and basically perform the inference. So yeah, at this point, the project is platform agnostic. Like this is basic C++ code, and you have no dependencies with Aidge. And here in the stat folder, we can see an image which we will show just here. This image just represents the memory management strategy that Aidge provide for this very simple network. So you will see the output of the first layer, FC1 gem, and with the time frame here. And so you will see that the peak memory usage is here, and you will see which output is generated, and you will see that here the output is reused, the memory is reused for the output of the next layer. So this is a nice way to visualize what's happening with your export. Now that we've generated a makefile and forward.cpp, we need a main file for running the export. If you already have an application, you don't really need this because you will just plug the forward header in your application. But here we don't have an application yet, so we will generate it with this function. This function just generated the main.cpp, which include like an input header containing the input tensor. And it will basically perform like call the forward function and print the outputs. So here you can see there's no dependencies to Aidge. And so yeah, basically optional. You can also generate other inputs if you want using this command, but we will not do it for the sake of this notebook. So just compiling using the make command and running the binary, we can see the outputs which are printed here and which are the same previously. A little bit of future features, like a glimpse of the future for export. We want to tackle heterogeneous export. So that means support target with different processing units, but also for the same processing unit, we want to generate code with different libraries. Another thing we want to support, and that we are going to support actually very soon in the future upcoming release, is the support for sub-int8 kernels for ARM export. And here you can see a glimpse of the performances. So we compare ourselves to SAMSysNN, which is a famous library for ARM Cortex-M models. And so you can see that for small kernel size of convolution, we are very comparable in terms of number of MAC per cycle, number of cycle per MAC. And you can see that we can also perform inference with 1 bit for the weight and 4 bit for the activation, which really allow to reduce the memory footprint and to export big models on very small targets, such as the H7, STM32H7 hardware. So yeah, thank you for your attention. I saw there was already some question in the chat. So I see Olivier is answering. If you have any question, please, we'll be happy to answer them. And I think I will end my presentation now.
Yes, thank you, Cyril, for the presentation. And I think we can continue with Luca, that is working at Thales.
Yes. So hello everyone. Today I will present you Thales' contribution to the Aidge platform. So to put a bit of context, I will briefly present TRT.
Is there
so
any
TRT is Thales
technical problem? I see.
Yes, sorry.
So you do not hear Luca?
Yes, we do.
Yeah, okay.
Can I continue, or is there any problem?
No, you can go on, please.
Okay. So at Thales and Thales Research and Technology, we are the research center of Thales. And so basically on this slide, you can find some numbers about our research activities. and currently TRT is engaged in many French or European collaborative research projects spanning many fields such as high-performance computing, quantum computing, or embedded AI. Therefore, we are particularly interested in new platforms for embedded AI, and this is why we aim to use and implement a new feature on Aidge. So yes, for the next slide, the first point is why we contribute to Aidge. In Thales, we identify the need for a sovereign and open AI design platform for some defense and sensitive application. Aidge open source nature and its capacity to be adapted to meet specific needs make it an ideal platform for some of our AI projects. One feature that particularly interests us is its ability to export model trained on popular framework like PyTorch. So basically, we have a model trained on PyTorch. We can easily convert to ONNX, and like Cyril talked about it previously, we can then export it on multiple hardware targets like CPU, DSP, or even GPU. And this feature ensuring versatility and efficiency in model deployment. So indeed, we have some use case with our global business unit, which brings their already trained deep learning model and basically ask us to implement it on embedded system. Thanks to Aidge, we can easily export the same model on various platforms, and therefore we can benchmark the different embedded systems, and we can easily ask their needs. So our initial contribution to Aidge have been focused on two key areas. So firstly, we have developed some quantization operators specifically for transformers. So the transformers architecture has some specific operators which were non-linear, and so basically we implement arithmetic approximation of these operators such as softmax and GLU. We implemented both backward and forward in order to allow quantization error training. Secondly, the second point is we have implemented an incremental learning pipeline within Aidge. This is particularly interesting as it allows models to learn continuously from new data, from new instances, without forgetting previously acquired knowledge, which is crucial for some Thales application, which require sometimes adaptability and longevity. On this slide, you can see some screenshots about the incremental learning tutorial that we implemented inside of Aidge. So basically, this tutorial is a Jupyter notebook that illustrates how functions our incremental learning feature. So basically, this tutorial explains how we use state-of-the-art methods such as data replay or knowledge distillation to limit catastrophic forgetting, which is the main problem in incremental learning. As our next step, we want to develop an object recognition demonstrator based on aerial imagery. This demonstrator will aim to exploit edge quantization and export features in order to implement a realistic Thales use case in an embedded system by using Aidge. So this concludes my presentation. Thanks for your attention.
Thank you, Lucas, for your testimony. And so now we can ask Christophe for this presentation. Yeah, thank you, Christophe.
Can you hear me?
Yes, very well.
Okay. So I'm Christophe Guillon from INRIA team in Grenoble. So INRIA is a national French institute for computer science and automation. And at the course team, we are working on several subjects, and in particular for this, I am contributing mainly to the program analysis and optimization group in the team. So I'm a research engineer at INRIA. So we contribute to the Edge platform on the compilation side. So here is a diagram from the Edge documentation, which shows basically the interaction between the different Edge modules. So basically on the left, you take some inputs, either generated by a standard framework or when NX graph views. You may also describe your model directly with Edge Python interface, as it has been demonstrated. You may interact because you have a data flow graph IR, which is directly executable. So you may execute it at any point, transform it, and optionally interact with other tools if you want for the training or possibly to optimize your graph, in addition to what exists in the Edge plugin. And then you have generally, at least for inference, most of the time, but it may be also for training, you have an export to also what is one of the objectives of Edge, an embedded platform. So you will, after graph transformation, export the code. So our contribution at INRIA is in this part. What we will contribute actually is compilation at the operator of subgraph level of what is exported. So it's complementary to what has been said before in terms of graph level optimization. You may then also optimize at operator level, for instance, or across operator if you make fusions. So we are working on this, basically optimized code generation. So more specifically, what we envision is basically this flow, which sorry is a bit complicated, but I will go step by step with an example. I have on the left non-NX graph, which I load into Edge. As I said, Edge provides an intermediate representation, which you can manipulate directly and execute at any time, which is also quite important, without lowering into another representation. So you have graph and graph subviews. It has been shown that you can match quite easily subviews of your graph or operator sets at compilation time. Basically, we have first a view scheduler that will, from a user-specified pattern matcher, select a set of views to be compiled, and we will interact then with the compiler and the graph views, and the scheduler may spin compilation operations and optimization operations. So at any time, you can first emit some of the default C++ templates provided by Edge, which are like the reference implementation in C++, which is the top level output that you see, the first green line. But otherwise, what we want to do is have basically an optimizing compiler assisted by an auto-tuner that will generate optimized code generation for operators or fusion operators. One of the challenges there is basically that the transformation space that is available to us is huge, and this is why generally you may have either user-specified constraints on the way the scheduling will be done, or user-specified strategies on how to optimize the code. But even without this, we may search into this transformation space and try to find the best configuration for compiling the operator. Concretely, for instance, it's activating vectorization, parallelizing loops, interchanging loops, etc. Compiler stuff. So we have an auto tuner basically that is able to train itself and to feed a performance predictor model that then we use to decide for the best optimization scenario. So for this, we may use execution on the host or on the board if it's for a cross-platform export. In the meantime, for augmenting the evaluation database and finding the performance predictor. So possibly, you may ask to have some operators that are optimized for speed first or for size first, or you may ask the auto tuner to find the best trade-off in between size, performance, possibly power, if there is some resources to compute power consumption, or at least to simulate it. So once the decisions on this graph has been done on what is the plan for optimization for all the operator and the subuse, basically, this is passed on the right to the optimizing exporter. So we see the compiler basically as an export plugin, which will, in fact, instead of just emitting C++ templates, will compile really the code with the compilation strategies that we have decided on the right, on the left. So on the right, you have an optimizing exporter, which is based on. Currently, we have several experimentals backend. At some point, we may decide what will be the main backend to use, but it may be a backend based on MLER compilers, for instance, or TVM backend, for instance. For now, we are several choices, but it's still a research on what is the best backend for what we want to do in the end. So it will emit a build system with optimized C code or optionally pre-built object code for the operator or the graph subuse, and of course you will flash this optionally to your board. What I haven't necessarily said is that basically the transformation space is huge and the distribution of the performance is very large. So on the top right, you have a distribution which is a log, so it is actually exponentially decreasing. And on the right, you have the high perf, on the left, the low perf. And you see that there are perhaps a dozen of transformations that gives the right performance above, I would say, 80% of the peak performance of the machine, while basically most of the transformation we may do are on the average performance. So generally, standard performance emitted by the compiler are in the range of 5 to 10% of the peak performance of a machine, optimized lead by around 20 to 50%, and with dedicated optimization for operators and subuse, we can reach up to sometime 80 or 90% of the machine peak performance. So this is the objective, trying to get the most in terms of performance from the compilation of the graph. Just to be noted before finishing on this slide, this is complementary with the graph transformations that can be still done directly on the graph. And what we want to keep is this vertical integration between the graph intermediate representation and the lower level compiler intermediate representation. So this is why we keep this link on the subuse on the graph. So in the end, for instance, the transformation and optimization scheme could be seen as annotations on the graph for the compiler then to decide how it will be compiled. So the graph representation of Aidge remains our main, basically, intermediate representation of work. Just to conclude, yes. Then what we have, so I have already mentioned many of the things. What is basically next for us is really re-emission of C++ from transform code. That is basically what you could see as a source-to-source transformation, such that the code can be auditable more easily. And then better integration to the fallback with neural network libraries or C++ templates selected by user, either it optimized with the compiler or with the standard libraries. And integrate multi-objective model, as I said, for embedded system, for instance, performance, size, and power optionally. That's it for me.
Yes, thank you, Christophe. So thank you all for participating in this webinar. So, and I hope this webinar gave you a good overview of the platform capabilities and perspectives. So please note that Eclipse Aidge is a platform under active construction, and I hope you will be highly interested in testing and joining this initiative that is innovative and collaborative. So please, you can follow us on LinkedIn to get some news, and you can also join us on Matrix to talk to the developer. So if you have any question, please you can contact us with this social network. So I think the event is finished now, and I thank you once again, and I hope you have a good day. So bye bye. Thank you.